It's my great pleasure to introduce Andrey Zhmoginov, who is a research software engineer at Google AI. He has a PhD in astrophysics from Princeton University 2012. He has been a postdoctoral researcher at UC Berkeley in the physics department from 2012 up until 2015. And he has been at Google AI since 2012. He has multiple great papers, highly cited papers in deep learning. And today he's going to be telling us about image understanding and image-to-image translation through the lens of information loss. So Andrey, the floor is yours.
Thank you very much for this introduction, and thank you very much again for inviting me. I'm very glad that this work that we've been doing is of interest to people, so it's very, very flattering. So yeah, today I wanted to talk about several things because I thought that while the most cited and maybe the most impactful work that I've ever done was contribution to the MobileNet v2, at the same time, I didn't want this talk to be solely about MobileNet v2 because there are way too many nitty-gritty details that may get us too far away from the overall picture. And so if we have time, I will also try to talk about several other projects that we've done, partly because I want people to maybe listen about other ideas that I think are important. And the overall overarching theme, I think, of this talk is explaining how I think thinking about different problems from the perspective of information flow, information conservation, or information loss can be important and very insightful. And of course, I would like to say that this all would not be possible without all of my collaborators, Mark Sandler, the main of them, and then a lot of other people who contributed to all of this work. So I will start with MobileNet v2, and very quickly I will try to explain why is it that we do this. So obviously these days, our mobile devices can do a lot of things, and it would be nice if instead of uploading your data on the cloud, all of the information processing could essentially be done on device. And so that's why, given the constraints that you have to really preserve the battery power, and at the same time you want predictions to be sufficiently accurate, you are forced to design networks that are as efficient as possible. And so this big subfield of, I'd say, deep neural network design is involved with coming up with these sort of architectures. So if you have maybe Google Lens, you will see that it's capable of doing this fine-grained classification. And I was also working a little bit on this device called Google Clips. And it's sort of a miraculous device that had a very small battery, but it was able to run for hours, basically doing real-time image recognition and running a lot of different models, figuring out, are people in the frame, how big the face that is in the frame, who is this person? So a lot of models basically running all the time. And obviously to do that, you have to have hardware that's very specialized, but at the same time, you have to be very careful about what these models are. And I will not get into the details about how exactly these different tasks are performed, because there is a classification task where you try to figure out what's in the image. There is an object detection problem where you try to figure out where exactly these objects are. There is just a general recognition problem where you may have face recognition or maybe landmark recognition, and many more. And what's important to know, though, is that for MobileNet models, for example, and for many others, they consist of this main chunk of the model that you can call like backbone. And then on top of this model, you put different heads depending on what type of task you want to perform. So if you want, for example, to do just classification, then you just produce a vector of logits that has the same number of dimensions that you have the number of classes. And then you just put like a cross-entropy loss on top of that. Or you might want to do like a triplet loss with embedding to do recognition of different objects, or you can have SSD and do object detection. But the crucial part is that the main body of your model is basically what I'm going to talk about, what constitutes the main part of it. So the MobileNet family is basically the family that was developed at Google for a sufficiently long time. And the first MobileNet v1 appeared in 2017. And even at that time, it tried to use basically the state-of-the-art techniques and advance on them that were available back then. But then since then, it gradually improved. Currently, it's MobileNet v3, and I think you heard a little bit about it already. I mainly will talk about MobileNet v1 and v2. And specifically, in MobileNet v1, there was a novel kind of component of the network called separable convolutions, novel at that time, that was introduced, and that actually helped to push performance. And then MobileNet v2 is also basically evolving around a single new modification, essentially replacing that previous separable convolutional layer with a new layer called like an inverted residual that I will get into. And basically after MobileNet v2, really began the era of neural architecture search. And at this point, people started kind of getting a little bit less hands-on when it comes to the design of a model. And at this point, machine learning algorithms started helping people really design individual components of the network, also taking into account specific device latencies. So I will talk a little bit more about this, but basically when you just compute the number of multiplications and additions that you need to compute to perform certain operations, that may be not proportional to the time that it would take on device at all. And when you design networks, sometimes it's very important to keep that in mind and actually optimize with respect to that. And obviously, MobileNet v3 added a bunch of other things like this self-attention sort of module and using better nonlinearities, et cetera, But as I said, today we will mostly talk about v1 and v2. Think of it as kind of a historical retrospective, like figuring out how this field evolved. So before going into details, I think it's worth mentioning, how do we even compare models? And at least at the time of MobileNet v2 and even in MobileNet v3, you will see the same sort of picture. It's very important to compare the models, assuming that they have, for example, the same number of parameters, or more importantly, they perform the same number of operations to perform computation. And that means that basically we frequently plot these points on two-dimensional plot where we have a number of operations on one axis, number of multiply adds, and accuracy on the other one. And we really try to figure out for a single model, if we scale it up and down, and we have certain ways of doing this, how does this frontier basically look? For example, in this picture, you can see that MobileNet v2 is above MobileNet v1. And even though you can take two different models, they will probably have different number of operations, different latency, and different accuracy. By just making this plot, you can clearly see which one is better. Again, it's important to notice here that it's real latency that's important, not simply the number of multiplications and additions. And for example, if you do on a mobile device, on a particular GPU, if you do a multiplication of smaller matrices, it might be significantly less operationally efficient than doing large multiplications. So that's something that is very important to keep in mind when you design models. And when you do this final evaluation, it's really important to make sure that you are not doing something that is very inefficient on that platform. So let me get a little bit deeper into this architecture. And the problem is I don't know how much people know about these maybe outdated deep neural network architectures. But for MobileNet v1, that was basically a sequence of layers that start with the input tensor. Usually, it's for convention, it's 224 by 224 by 3. And then as you go deeper into the network, you see that your image resolution decreases frequently by a factor of 2. And then at the same time, the number of channels of each tensor goes up and up and up. So essentially, the dimensionality, the total number of activations in each tensor goes down, but the number of channels grows up. And in MobileNet v1 time, it was recognized that, depending on your circumstances, you might want the models to run a little bit faster, maybe sacrificing a little bit of accuracy. And so at that time, it was really popularized to use so-called width multipliers, where you basically scale the number of channels in every layer uniformly in such a way that if you scale it maybe by a factor of 2, you will get an overall acceleration roughly maybe by a factor of 4. You can do the same thing with image resolution. If you decrease the input image resolution, then you of course have to retrain the model, but the model that you will get will essentially, if you decrease the resolution by a factor of 2, it will effectively run 4 times faster. And again, you will of course see degradation of performance, but it might be worth it, and especially if you have a particular task in mind. And for full MobileNet V1, V2 models, on modern day devices, you can expect latencies of order of like 100 milliseconds. So in principle, it can run almost real time. Of course, it will probably mean that it will drain your phone power, your phone battery pretty quickly, but it's definitely capable of like achieving very, very low latencies. And if you reduce resolution, then of course you can increase the speed of processing further. Another important detail that I just wanted to mention is that quantization is also important. So floating point number operations are not as fast and as efficient, maybe as simple integer like 8-bit integer operations. And so that's why when you see any model that is executed on device, it's very likely that it will be quantized to at least 8 bits. Sometimes some architectures allow even smaller, and in the limit you can have 4 and maybe even 2. So it becomes a very interesting type of model and calculation, but definitely allows you to run much faster. And again, since I got a feeling that I should maybe talk a little bit more about details, when it comes to quantization, I don't know if you know this, but the old approach was basically to pre-train a model, have it work in floating point numbers, and then quantize it post factum after you trained it. But that led to a significant degradation of performance. And so after that, in TensorFlow, you can see this, and in many other platforms, that people start adding simulations of quantization directly in the graph, in your model, so that you can basically train your model, and it will be aware of the quantization operations, and it will actually, roughly speaking, try to adhere to the fact that you have quantized tensors. So I mentioned all this, but the main part of the MobileNet V1 model was separable convolutions. And again, I don't know how well aware people are of what this is, but I thought that I would quickly go over it. The idea is that a conventional convolution, like shown at the top, is essentially specified by you can say by 4-dimensional tensor. You have 2 spatial dimensions, and you have dimensions that correspond to input channels and the output channels. So basically, for every input channel and output channel, you have its own private spatial kernel. But the problem is that it's very heavy, and you generally need this image size times kernel size times input channels times output channels number of iterations. That can be a huge number. So one of the tricks to reduce it is to factorize this weight tensor. And of course, it becomes a special case, less general case than just using convolution. But at the same time, it can be much more efficient in the sense that you may need a lot less operations to actually perform computation. So in this case, you basically take this 4-dimensional tensor W and you decompose it as a depth-wise convolution that basically takes every channel, every input channel, and for this input channel performs a single spatial convolution. And then this operation is followed by a point-wise convolution, which is basically a conventional 1-by-1 convolutional operator, which maps every input channel to every output channel. And if you look at the savings that you get, it essentially allows you to save roughly the kernel size scale. So if you have a kernel which is 3-by-3, then you can, roughly speaking, run this model almost 9 times faster, because 3-by-3 is 9, and that's the kernel size, and that's a very significant speed up. But if you actually perform experiments and look how much you lose because of using separable convolutions, then it turns out that on full model ImageNet 1000 class accuracy falls down by just about 1%. So that huge speed up given to you by this special structure of your convolution allows you to speed up the computation very significantly. And so one extra detail that I wanted to mention is that, again, people do experiments and try to see, well, maybe instead of doing this first depth-wise linear convolution and then follow it up by point-wise convolution, maybe we should add something in between. And as experimental results show, it does make sense to add a nonlinearity between these 2 operations. And so the full single block for MobileNet V1 architecture is basically shown on the right. And it consists of, like I said, 3x3 depthwise convolution. Then you have batch normalization operation and ReLU nonlinearity for mobile at V1. And then that is followed up by a 1x1 convolution. And then finally, you again do batch normalization and ReLU as you would do in a conventional convolution, just trying to make it nonlinear. So this block is basically the main design block behind mobile at V1. When you go to, at that time, like this model was actually very well performing, and it was really a state-of-the-art model at the time. When we started working on mobile at V2, we didn't change that much. We basically kept the overall structure of the model kind of unchanged. You still have, in the very same way, you have a sequence of layers, each performing a single operation, essentially, very similar operations. But we replaced this block structure. And by doing so, basically, we optimized each individual layer, essentially ending up with a much more efficient model. And the most important thing about this structure was really in this bottleneck layer, or if you look in the paper, it's called inverted residuals with linear bottleneck, and I will explain why. So now I will not talk much about the specific image sizes and number of channels, but I will talk more about the inverted residual and what was the kind of the motivation behind it. And I should add that I was asked about this, that MobileNet V1 and MobileNet V2 models, we ran a lot of experiments, hundreds easily. And each experiment, if you run it, even like previously we ran them on GPUs, it could take you up to a week to train the model and make sure that you train it fully and being able to carefully compare it with other pre-trained models. So it's actually extremely, extremely power and time consuming process. So the hope is, because these models are executed, hopefully thousands, millions of times a day, all that power consumed by us training these models will be offset by the efficiency of these models, and that we don't have to, that will save power when we do every single inference. But of course, like, one has to keep in mind that this careful fine-tuning, this careful exploration of this space would not be possible without availability of accelerators that you can run for days and days and weeks and months and months. Nowadays, we train on TPUs, and that actually, with additional tricks, you can train a model actually essentially in an hour. And after using a bunch of tricks, we could reduce the time of training previous models on GPUs also to basically a single day. But it was still a considerable amount of time. Okay, so I hope I a little bit clarified that point. But so what is inverted residual, and how we actually ended up designing it, conducting hundreds of experiments? So the idea was actually very, very simple, I think. So think about the previous generation of model, MobileNet V1. So in MobileNet V1, like I mentioned, you have a separable convolution that maps from n-channel tensor to an n-channel tensor. And of course, to describe this, you basically need O of n squared, parameters and O of n squared operations to perform this computation, mapping from n input channels to n output channels. But what if you add a bottleneck between these two tensors? What if you first take your n channels and map them into h channels, and then you map a tensor with h channels back to n channels? Well, you replace n squared essentially with two nh operations. And of course, it doesn't make sense if your h is greater than half of n. But if it's smaller, and if it's significantly smaller, then you actually might save a lot of computation by doing so. And basically, this again can be represented as just a simple matrix decomposition where you represent your original, fully connected layer that maps from K to M channels as K to H, H to M. So the expression shows it there. And of course, in principle, the smaller this H becomes, the fewer and fewer operations you have to perform. But obviously, you cannot reduce H too much. And so this bottleneck, the smaller it becomes, if your network is not deep enough, if operations are not expressive enough, very, very roughly speaking, your image manifold will just no longer fit in that H channel tensor. And what you will have as a result is that a lot of different images might end up being mapped into basically the same activations in your hidden layers. And as soon as that happens, as soon as you have two different input tensors mapping to the same output tensor, that's all. You can never distinguish them again. So it was important for us to actually preserve that information and avoid, avoid bottlenecks that start mapping very different inputs to the same outputs. Okay, and so in practice, actually, this bottleneck size is about 1/6 of the image, of the number of channels that N has. So if you combine this idea of a bottleneck with a separable convolution, then basically this is what you get. And this is a picture you can frequently see in MobileNet papers. So I wanted to explain it better. So first you have basically a depth-wise convolution. And it's shown because you take a 3x3 image region, and for every input channel, you perform a convolution independently. So you end up with a tensor that has the same number of channels. But then at this point, you have a pointwise convolution. So basically, you have a convolution with a kernel size 1x1, but you use again the ReLU nonlinearity, and you map to a much smaller tensor size. Again, basically 6 times smaller. After you do this, you do the mapping again 1x1 convolution, but this time without the nonlinearity, back to again the original large tensor size. And this block is basically the core of the MobileNet V2 model. The fun thing is that you can also maybe look at this at a slightly different angle, and instead of thinking about it as going from large tensor to small tensor, small bottleneck, back to large, you can also think about it as going from small tensor to large tensor and back to small tensor. And this is kind of gives you a slightly different perspective, again, very hand wavy, but you can think again of this input tensor H as being a small bottleneck that hardly feeds your input image manifold. But then if you really want an expressive transformation from this H input tensor to H output tensor, you better have a sufficiently large hidden layer between them. So you can think of it now as an expansion layer. And the bigger it is, it's followed by nonlinearity, the bigger it is, the more expressive functions you can represent this way. And so that was another hand-wavy way of explaining how this architecture comes to be. Basically, you try to reduce the size of your tensors as much as possible. But to still allow the model to be sufficiently expressive, you have to add these intermediate expansion layers to make sure that the functions are expressive enough. And even more than expressive, it's also important that they don't lose that much information in the process. And this is stressed out in the original paper. And the very simple picture is, again, if you have a two-dimensional manifold, for example, that you apply ReLU to a two-dimensional manifold in a two-dimensional space, then yes, everything with negative coordinates will basically get mapped to zeros. And a lot of input tensors will end up mapped to a tensor 0, 0. But you may not want that. You may want to preserve that information. And one of the ways to do that is to maybe map your input tensor to a higher dimensional space and then apply ReLU nonlinearity there. And again, as it turns out, that actually works. And you can see this. This is a very simple but very visual example where you take a two-dimensional spiral in the input space, and then you map it to a higher dimensional space. You apply ReLU nonlinearity, and then you apply an inverse transformation, mapping it back to 2 dimensions. And what you see is very intuitive. If your dimensionality of the space where you map is also 2, then of course you will lose a lot of information because ReLU cuts out huge chunks of your input distribution. But as you increase the resolution, your transformation becomes more and more complex, and eventually it becomes a very high probability one-to-one transformation. So you end up with some very non-trivial mapping that at the same time is still one-to-one, and you don't lose anything in the process. So I think that, it's very hand-wavy explanation. It's not mathematically rigorous or anything, but it provides you a very good explanation of why it happens and the design motivation for making these layers look like they do. So I explained the motivation behind the bottleneck or the expansion, which is the same thing, just looks from a slightly different angle. And then, of course, again, something that you don't see in the paper, but something that we had to do you start with this idea and then you ask a question, okay, what happens if I now change this? What if I add a residual connection, because we know that residual connections are helpful? What if I add more nonlinearities? What if I add a residual connection not between smaller tensors, for example, like shown here, but between large tensors? And so we conducted lots and lots of experiments, basically trying to answer these questions. And the final design that you can find in the paper and that I showed here, that basically we have this residual connection between smaller tensors and this expansion layer. This final design was motivated by, again, hundreds of experiments. And you can see, for example, that if you just simply remove a residual connection, your accuracy on ImageNet drops quite dramatically. You can see like a 2% decrease, which is in these circles a big deal. And similarly, if you add another value nonlinearity, for example, on smaller bottleneck tensors, then yes, as you expect, again, maybe you lost some information. And as a result, your accuracy also drops, and it can drop actually much more dramatically for smaller networks. And so ultimately, yes, this is the core of the design of the MobileNet v2. I think even when Mark Sandler, another co-author, kind of explains MobileNet v2 architecture, he also explains it from this perspective, trying to explain kind of the intuition behind why it works and what it does. I think at this point, I wanted very quickly to, again, reiterate that, right after MobileNet v2, we saw a huge number of papers that started doing neural architecture search. And on top of ShuffleNet, which was not neural architecture search, we saw, different papers like NASNet, NASNetNet, NetAdapt, and eventually MobileNet v3, which was published in 2019, that use now neural architecture search. And now you have to be very careful. You basically take a real device, you take a particular phone, you measure very carefully the cost of every operation depending on its inputs. Like, what are the dimensions of the input tensors? You tabulate the data, and now using those tables that actually contain a lot of information about how this piece of hardware actually works, you run now automated architecture search to optimize as much about this architecture as you can. And finally, nowadays, it seems that image transformers are also becoming competitive in that efficiency space. So who knows, maybe there is something, and these types of novel architectures will actually make new architecture much, much more efficient in the future as well. So I definitely hope that this is going to happen. And looking at this, this is a plot from MobileNet v3, and basically you can see that with MobileNet v3, I think that's really, at this point, it's really the best state-of-the-art architecture, at least at the state 2020 when I looked at it. And you can see that it outperforms MobileNet v2, and it definitely is on par with NASNet and other similar models. So I guess I thought that maybe this wraps up MobileNet v2 part, but maybe it's unconventional, but I want everybody to get as much as they hope to get from this part. So if there are any questions at this point, or maybe if you want me to talk about something in particular, I can maybe get a little bit more in-depth into any subject related to MobileNet v1 or MobileNet v2, or maybe transition to v3. So if anybody has any questions now.
I do have a question.
Mm-hmm.
So when you use these mobile nets, do they only help during inference time, or do they also make your training time shorter compared to like ResNet and the other very large models?
Right. Yeah, they are definitely helping. You will definitely have training which is faster. Simply because, again, roughly speaking, you can think of it this way. If inference time on mobile device is smaller and more efficient, usually that means that it translates to GPU performance when we train these models too. It's not always the rule, but we saw it being that way. And so MobileNet v1 definitely trains very fast compared to much bigger models, like, again, and compared to ResNets as well. And if you look, for example, at other models, you can see here that, maybe somewhat outdated models, but you can see here, oh, it was not an inception model, for example, right? It is significantly more expensive to both do inference and to train with. And so the fact that this model is so fast actually helped us not only to train it, but I also, when in my day-to-day life, I do different kinds of experiments with mobile architectures, and not only mobile architectures, I'm sorry, other architectures as well. I frequently choose mobile because they are also more efficient to train compared to other alternatives. If you want really a very, very good accuracy, then you might at some point have to go either to very high multipliers, what I mentioned, like with multiplier, or you may want to try other models as well. But it definitely helps to iterate faster to use these models.
Cool. And just one more question. So, like, there was an idea of knowledge distillation to transfer the knowledge from a large model to a small model. Like, is there any chance to get like the accuracy of like Inception V2 on MobileNet version 1 with using this type of I don't know, knowledge distillations?
I would not be able to answer this exactly, but definitely, I mean, whatever we do, we definitely see a huge spike in accuracy due to distillation. So you definitely can expect, very roughly speaking, to get several % accuracy boost out of this if we're speaking about ImageNet specifically. You may not, what we saw is that, we did certain experiments with, in a recent paper, but sometimes you can, in practice, if the models are at least somewhat compatible, you can see compatible accuracies in the end. I'm sorry, I will not be able to provide like very specific numerical answer, but I guess my general advice is, yes, you definitely want to try to do that. It may not help you to reach the accuracy of a big model, obviously, especially if it's much more complex, but you will definitely gain a non-trivial amount for your smaller model generally.
Cool. Thank you.
All right. So again, I will be happy to answer any more questions about this, very practical part of the talk. But I wanted to add something maybe a little bit more whimsical and entertaining to it. But again, kind of staying in that framework of information and how it propagates in neural networks and what happens to it in the process. So one of the fun things that we did was related to cycle GANs. And recently there was a lot of interest in reversible generative models. It's basically the models that on every, they involve a lot of transformations, a lot of, again, you can think of them as layers, each of which is essentially one-to-one mapping. So you don't lose information while you do this. And CycleGAN is not a model like this, but it had a very similar concept of a cycle consistency loss in it. I will explain in a second what it means. But basically, it tried to preserve information. And that led to very, very interesting phenomena, which I want to kind of discuss now. So the CycleGAN is basically an unpaired image-to-image translation model. What this means is that you give it a bunch of images from one distribution, P of A, and then you give it a bunch of images from a different distribution. They are not paired in any way. So that one could be, for example, images of horses, and another image domain is images of zebras. And then you want to train two transformations from domain A to domain B and from domain B to domain A, such that if you take any image from domain A and you apply a map, you get a realistic image from domain B, and vice versa. So it kind of allows you to do this natural transformation between different domains. And the results that CycleGAN got were extremely nice and very, very appealing. Like some of them are shown here, but you can see that the model being presented with examples of zebras and horses, again, was able to figure out that it needs to remove or add these zebra stripes to convert one animal into the other. Or if you show it, real photos and maybe stylistic images or paintings, it would learn to make this transformation. So the performance of this model was spectacular. And the way that authors managed to train this model, as maybe the name suggests, is using the main idea of a GAN, which means that basically you have for both of these domains, which I now call X and Y, and I'm sorry for change of notation, for each of the domains, you have a discriminator. that basically looks at real samples and it looks at generated samples. And you train this discriminator to discriminate between these two types of images. But at the same time, when you train these mappings from domain X to domain Y and from domain Y to domain X, you also want to make sure that they fool the discriminators, the corresponding discriminators. So basically, if you convert a horse to a zebra, you want to fool the discriminator that is specialized in zebras to think that, oh yes, it's probably a zebra. So that's basically one of the components of this model, a simple, like a conventional GAN objective. But at the same time, the authors added this another component called cyclic consistency objective. And the idea behind it is that if you take an image from domain X and you map it to a domain Y, and then you map it backwards to domain X, you will end up with the very same image that you started with. The nice thing about this loss is that it basically gives you per pixel image supervision, something that discriminator cannot give you. And so it actually helped to stabilize the model and really get those nice kind of state-of-the-art, nice looking results. But if you think about this, what this cyclic consistency loss actually implies is that a composition of G and F, or F and G, is roughly speaking an identity matrix, identity transformation. So you don't lose information when you go from domain X to domain Y and then back to domain X. And if you think about this, sometimes it may be very non-trivial how this is even possible. Imagine, for example, that you have this famous data set where you have aerial images, so images taken by satellite of a city, and then you have a corresponding Google map. So it's very easy to see that aerial images have a lot more detail, and so kind of the information content, the entropy, if you will, of those images is a lot higher than the entropy of the maps. But at the same time, the cyclic consistency loss that you would have if you train this cycle again would require that you preserve the information that is contained in those aerial images. So the real question is, how would that be possible? And if you train this cycle again, you will indeed see that, oh, it trains perfectly. You will see good results in the sense that if you take an aerial image and you convert it to a map, well, this map actually makes sense. You see outlines of buildings, you will see roads, you will see parks when they are, maybe not in this example, but generally you will see them. And so it seems like it does the job that it was supposed to do. But sometimes it looks like maybe it does this job too well, in a sense that if you, for example, look at certain roofs, the structures of these roofs will be preserved, right? So it's not seen anywhere in the map, but you still can recover it in the final image. So basically you take input image, you map it to maps, and then you map it back, and the same structure reappears. So how is this even possible? And the obvious answer is it's possible because CycleGAN becomes really good at hiding this information. It's basically learning to encode information about this about this detail in the original image in this very high frequency noise. It's very low amplitude, so with a naked eye, you will not be able to see it. But if you subtract maybe a mean from every region of your image, you will see that on the right, you see a conventional map, and you will see that it's actually very homogeneous, right? Like the colors are uniform. But if you look at the image produced by the CycleGAN model, you will see that there are a lot of these high frequency strange details, and it's been amplified to really show the high frequency noise that CycleGAN adds. And so the bottom line is it's kind of non-trivial, but it was non-trivial to us when we saw this at first. But yes, CycleGAN becomes extremely good at hiding this information. So essentially, you can say that it cheats a little bit. And this is, given my physics background, I like to think about it this way, that essentially imagine that you have different manifolds, different dimensional manifolds. Maybe aerial photos are higher dimensional and maps are lower dimensional because you have a lot more restrictions. You want to have uniform colors. So the map F, when it maps, a certain image to a different image, it effectively has to reduce the dimensionality of the manifold, which means it has to essentially contract the image domain a little bit along certain dimensions. And so if you look at the eigenvalues of the Jacobian matrix, you expect that the eigenvalues will be small, at least for some dimensions. But the map that maps it back to the original space then has to again expand them, which means that it has to have very high values of eigenvalues in the corresponding Jacobians. But what this means is that F transformation is fine, but the G transformation becomes extremely sensitive to where you are in the input space, on the map space. Well, you may say, okay, so what? Okay, it's sensitive. Does it mean anything? And the unfortunate fact is, yes, it does mean something. It means, for example, that you have to be very careful about what you do with the generated images. Because if you take your original aerial photo and you map it to the maps and you get a map, which you can see is maybe not exactly accurate. When you map it back to the aerial image domain, you will see that it preserved everything. Again, detail on the roofs, little roads, everything is preserved. But if you do something as simple as add a JPEG compression to that map, you will immediately have an entirely different result, even if visually you will not be able to tell those images apart. I mean, the original map images. But after you pass them through G, all of a sudden, buildings may disappear. You will completely lose the structure on the roofs. You may even lose a lot of information about parks, etc. So that's an important consideration one. Now your map is very sensitive, and basically, if you were to use, lossless compression on original images and on generated images, on generated maps, you would see that their, lossless compressed size should be about the same. Whereas previously, if you just look at real Google Maps images, they obviously contain much less information, and so lossless compression would probably be much more efficient. So that's that. But the story doesn't end there. And another interesting thing is that because the map is so sensitive, because the map from maps to aerial images is so sensitive, it becomes extremely easy to attack adversarially. So what I mean by this is that imagine that you take some map and then you take some target aerial photo that you want to get out, right? The target photo is X and the original map is Y0. And what you're trying to solve is you want to find a map, a map, Y star, Y star, that is really close to Y0 and looks almost indistinguishable. But after you apply G to it, that transformation that we learned in Cyclic, it produces you the image that you want. And maybe it's not surprising that it's capable to do this where the map and the aerial image are really similar and come from the same essential environment. But what's interesting is that they can be completely different. You can start with a map that has nothing to do with the aerial image that you want to generate. And then the algorithm, the adversarial attack, can find you an image that looks this Y star that looks almost indistinguishable from Y0, and that's the bottom row. And when you apply G to that Y star, you basically reconstruct the map that you wanted to reconstruct, even though this map doesn't make much sense to a human because you have a park in one place and now you have buildings there. So again, one potentially very important implication is that by trying to preserve information, but not being careful with effective entropies in these domains A and B, you ended up training a model that becomes extremely susceptible to adversarial attacks. So for us, that was a very, very cute and just interesting observation. We had a lot of fun just playing with this model. You can also do a lot of interesting things like taking maybe different aerial images with trees located in different parts. And because of approximate linearity of the transformation, you could basically very quickly construct an image that has trees in both of these locations. And you could do a lot of trickery similar to this, like moving features, etc., etc. So so I guess the takeaways from this part is that if your image domains have very different, or any domains have very different complexity, but somehow you still want to have an invertible map from one to another, then you should be prepared to see a lot of very interesting and unusual things happen. And in this particular case, like we definitely saw susceptibility to adversarial attacks and just extreme sensitivity to inputs. All right, well, that's part 2. I still have part 3, but only 5 minutes. So what I'm going to do is I will just say a few words and then I will finish at exactly the time I need to finish. But it's just the final thing, but maybe complement the MobileNet discussion. In MobileNet, I mentioned the information bottleneck, and I said that, that intermediate tensors, if you reduce them too much, then you will start losing information. So it turns out that people actually thought about this before, and they tried to approach this from a purely information theoretic point of view. And I'm talking about Tishby's work in 1999 that really started kind of these sort of approaches from information theory, applying them to a field of deep learning. The most obvious, maybe not obvious, but the most common setting is where you have maybe a conventional classifier. So you basically have a joint distribution on your input samples and your class labels, Y. And what you want to do is, like in any deep learning setting, you want to learn this encoding of the input, Z, from which you can then reconstruct the label. Right? So what you do is essentially you learn a conditional distribution function, P of Z given X, and it's parameterized by deep neural network parameters theta. And now you can ask yourself, okay, so I have a deep neural network that takes X as input and produces Z as output. And I want a Z to be predictive of the label. What conditions, what information theoretic conditions do I have to impose? And the obvious answer is, well, okay, first of all, you want the mutual information between the encoding and between the label to be maximized, which is basically another way of saying that I want the information about the label to still be contained in Z. But if you want only that, then the solution is trivial. You take Z equals X. So you basically preserve all of the information, and you did that job. So obviously, you don't want to preserve all of the information. You maybe want to shed some information that is not helpful at all. For example, if you have a model classifying cats versus dogs, you don't care about how many blades of grass are in the image, right? So that means that you want to reduce the amount of information contained in that encoding. And one of the ways to do that is basically to maximize the mutual information between Z and Y while having a limit on how much information you have in common between the input and the encoding. So by having basically a bound on mutual information between X and Z. Another way of basically just reformulating this optimization objective is a single optimization objective where you have Lagrange multiplier beta, and you basically just you are trying to maximize this expression, right? Which at the same time will maximize the mutual information between Z and Y and minimize the mutual information between X and Z. I'm almost done. So recently there was a variational information bottleneck work that tried to show how it's possible to do this for deep neural network architectures, because generally this optimization objective is really difficult to optimize for complex architectures. And they proposed a bunch of techniques that you can use to essentially put variational bounds on quantities that you see in this expression and essentially optimize them. So figure out, basically, instead of optimizing cross entropy loss, you end up optimizing a different objective. But when you do this, you end up getting a very nice encoding and basically a very nice classifier that has these additional advantages, as they show, like not being as susceptible to adversarial attacks as maybe a conventional classifier would be, and many others. And so in the work that I have absolutely no time to discuss, I just wanted to say that you can think about these sort of objectives and apply them to domains where people haven't maybe applied them before. And I'm not claiming that I'm like absolutely first one who thought about this, but we were one of the first ones to ask a question. Can you apply this objective to learn about images? Basically, what is responsible in that image for making this image have a particular label? And just to give you an example, like you might have a data set of cats and dogs, and you have a label for an image, whether there is a cat or a dog there. And the point is, if you see sufficiently many of them, soon enough, you might be able to say that, oh, I never was told what the cat is. But given that I see these labeled images, I assume that this is a cat, this object is a cat. And this is particularly important for maybe medical imaging, where you have labeled images. Maybe the patient is sick or the patient is healthy, but you don't know what you have to look in this image to figure that out. What's this feature that tells me that the person is sick? And methods that look at salient regions can actually help you answer this question. And all I wanted to talk about was basically how you can apply the same information bottleneck objective to figure that out. And if you're interested, yeah, we published the work. It's not the best way to do that. That's a way to do that. But I thought it was sufficiently cute and interesting, especially in the sense that it takes that information bottleneck objective and shows how you can apply it to do a seemingly completely different task. And yeah, I think at this point I will stop. But the very final concluding remark that I wanted to add is that sometimes it's helpful to not get too deep into the forest, right? Sometimes you want to think about problems from maybe very general point of view, from basically first principle point of view. And it definitely helped me. And it's always nice to revisit your work and ask questions like, but what does this mean in terms of the information, how it propagates through this model? Or what does it mean, for example, like, is this function invertible again or not? Like, or what implications of these are? I had a bunch of these simple principles, but you can think of them. There are very, very many that you can apply to very different problems and discover something interesting about them. And it can actually lead your choice of how to design a model. It can tell you something about peculiar behavioral models, or it can help you to come up with a completely new method for doing something like, again, salient region discovery. So that's it. Thank you very much for your attention. I'm sorry I didn't have time to cover everything, but I tried to do a good job on the first two, at least.